Good morning. Today is we're going to review these practice exams, but first you have homework due on Friday for Chapter 3. Does anybody have any questions over that homework assignment? Yes?
Number 16, are we supposed to be solving constants in it?
Which number was that?
Number 29.
Okay.
Sorry.
You should be getting a expression which gives the different probabilities as a function of the energy, the temperature. You aren't actually supposed to get numbers for the values, because I don't think all the data is given. Other questions? We're just asking for questions on the homework, if you guys have any. All right, remember, yes?
We did the last one on homework.
The last one on the homework. Okay, 3.48?
Yeah, I think it's 4. Yeah, 48.
Okay. So did you have any sort of specific question? Let me just, while you're getting your step out, let me just go through. Your body must dissipate energy from metabolism at a rate of 100 watts by various mechanisms. Suppose that the mechanism stopped working. At what rate will your body increase? Okay, so this is going to be very similar to something that we talked about in class, where you're going to have a rate of increase, so a rate of energy per unit time, and you're going to then rate the change in internal energy, which is your metabolic rate, with the change in temperature using the heat capacity. So you're going to be able to then solve for the change in temperature. Basically, it's going to be the metabolic rate divided by the heat capacity. So you're going to be able to get the rate, and then you can just multiply by time to get how much energy is required. So you can either look back in your notes on the day we talked about heat capacity. We did almost that exact problem. Or you can just sort of follow those steps. But if you had something more specific, I'd be happy to try to address it.
I guess, because the equation for heat capacity is C equal Q over difference in temperature.
Okay.
So you use that for the first one? Because I thought, the first one would be at a rate of 100 watts, since, your metabolism was working at 100 watts, and now it's not.
Well, you have for your, that's what you basically just said, your energy is heat capacity times temperature. So what you can do is you can say, well, the rate is going to be per unit time. So now this is really your metabolic rate in watts, because watts is joule per second. So that's your metabolic rate, and what you're looking for is really this rate. How fast is it increasing in time? How fast is the temperature increasing? Because it asks for at what rate will your body temperature increase? So you really just take your metabolic rate, and you're going to divide it by your heat capacity, and you should be able to then get that rate. And then if you want to find how much heat overall, or how much temperature increase overall for a certain amount of time, you just multiply by the rate by the time you're interested in, and you got to be able to calculate the total temperature increase. So that's the key, is that you treat these as rates, and then you get that relationship still holds. Other questions? Yes.
For 30, how would you set up the probabilities of the correct matchup versus the incorrect?
For 30. Okay, so you're going to have, this is a DNA problem. You're going to have a certain energy associated with when DNA binds correctly, and you're going to have a certain energy when DNA doesn't bind correctly. So it's really a two-state system. And it doesn't so much matter what the energy of the lower state is. What's important is that the energy of the upper state's a little higher. And you can work out and figure the ratio of those probabilities. If you figure the ratio of the probabilities, you can find then any constants will cancel out, and really this big factor of E will cancel out, and it really will only depend on the difference between the energy levels. So you're going to set it up like we do for a lot of the Boltzmann constant problems, And the key is you want to look for a ratio of probabilities. So you can say the probability of an error is equal to the probability of being correct. This is going to be essentially 1 in this case because the probability of an error is real small, times a factor, a ultimate factor, just involving this little extra energy. Does that clarify your question?
Yeah, I would say so.
Okay. That's an interesting problem because it gives you some insight into what's actually driving some of the mutations. Not everything. Some mutations are caused by radioactive interactions that don't depend on temperature. But even if there was nothing else other than just temperature, you'd still get some thermal mutations like this. Okay, if you want to have your homework to study for exam 1, which is coming up on Monday, make sure that you make a copy of it because you'll get the solution back, but not your graded homework back before the exam. Okay. So, next task is to look at the practice exam, and we'll start with practice exam 1A, and let's just go through it. Notice, like I said before, there's a bunch of material at the top, which is a bunch of information, constant values, unit conversions, all that will be at the top of the actual exam. So, short answer. Okay, short answer questions, there will be 4 of them, just like on the practice exam. These are all or nothing, so there's no partial credit involved. What is the diameter of the HIV virus? So who could tell me what the diameter of HIV is? 120 nanometers is actually correct. Right on the button. Now, I'm not expecting you to actually remember 120 specifically, but you should know that viruses are usually on the order of 100 nanometers, 1/10 of a micron. And it says here that any answer within the factor of 5 is acceptable. So if you gave me anything from 24 nanometers up to 600 nanometers, which covers just about every possible virus, you should be okay. So be aware, I'm trying to get order of magnitude, and I'll give you a hint. I'm not going to select some sort of example that's really different than the standard. Because I'm not going to try to look up the very smallest virus in the world and figure out, I'll try to fool you. And I'm going to try to pick typical examples so you just kind of have some general sizes to know. Okay, so what is the length of a mitochondrion?
2 micrometers.
2 micrometers is basically the length. Remember, mitochondria is a subcellular element. They're about the same as bacteria. So again, anything from 0.4 to 10 microns would be acceptable. So you could answer 8 microns and you'd get full credit. You could answer 12 microns, you get 0 credit. I mean, it's sort of a all or nothing thing within that window. But basically, when you think mitochondria, you ought to think bacteria. And bacteria are on the order of microns. If you just remember that much, you should be okay. Okay, now I'm expecting you, I gave you some equations to know, but also there's some basic definitions. So problem 3 is sort of a definition hidden in units. What are the units of heat capacity? And we already got them written up on the board, but what would the units of heat capacity be?
Joules per Kelvin.
It's going to be joules per Kelvin. If you answered calories per degree centigrade, I'd probably have to give it to you. If you wanted to be a wise guy and you answered ergs per degree Rankine, I'd probably still give it to you. But it's basically energy over temperature. And if you're sticking with the SI units, that'd be joules over Kelvin. But do note that since it's a change in temperature, it could be degrees Celsius as well as Kelvin. Either way will give you the same results. It's only when you get the temperature by itself that you have to worry about absolute temperatures. Now, problem number 4 is asking you a specific rate for mammals. A few of these questions for short answer might involve some small calculations. This is an example of one. Most of them won't, but some might. So the specific metabolic rate of animals is, as a function of mass, is given P is proportional to M to the -1/4. So I'm going to write it as a constant M to the minus 1/4, or minus 0.25. And you have a 500 kilogram cow, and it has a metabolic rate of, and here I'm using P, I used R in class, just a symbol, but I specifically say what is metabolic rate. So P is 15, and this also has kind of funny units, kilocalorie per day, a kilogram. So what's the expected metabolic rate of a 50-gram mouse? Okay, you're trying to find P. Who can think of a good way to start doing that? What would be the first thing you might want to try?
Set up a ratio.
Yeah, in this case you set up a ratio. So we're going to say P cow over P mouse equals C's, which are going to cancel, so that's nice. And you're going to get M cow over M mouse to the minus 1/4. And since we're interested in what P mouse is, we're going to find that P mouse is equal to P to the cow times M, and now you're taking this and it becomes a positive when I bring it to the other side, because I'm bringing it to the other side to get P mouse, so it's going to become plus 1/4. Okay, we're almost there, but there's still a few tricky things. Now you could kind of get all worked up about funny units here and start doing a bunch of conversions. But the nice thing about writing it in this way with the ratios is that the units don't matter what you use as long as you're using consistent units. So if you know what P cow is in kilocalories per day kilogram, you can just easily get P mouse in the same units. And since I didn't ask for any specific units, did I? No, you guys should just give it to me in the same units, so there's no unit conversions. What do I use for the mass? So that's going to be 15 with these units. What's the mass of the cow? 500. What do I use for the mass of the mouse?
0.05 kilograms.
Yeah, this is where you have to be careful. You can't just put in 50 grams. That doesn't matter what units you use for the mass here, but they have to be the same units. That's the only rule, because some of them to cancel out. So you're either going to have to convert cow to grams or mouse to kilograms. If we convert mouse to kilograms, we get 0.05 to the 1/4. And this gives 15 times, let's see, the 5's cancel, that's 1, 2, so that's going to be 5, 0, 0, 0, 0. Not 5, 1, 0, 0, 0 to the 1/4. Okay, now you can either pull out your calculator, or can anybody tell me what this becomes right away? 10. This is 10 to the 4th. If you take 10 to the 4th and raise it to the 1/4, that's the same as 10 to the 4 times 1/4, or 10 to the 1. So this becomes just a factor of 10. So you immediately get 150 kilocalories per day kilogram. So if your calculator did crap out, you could either, one, come up and ask me to borrow mine, because I'll bring mine, or you can do this one in your head without a calculator, just because I use really nice numbers, so there's no problem taking a fourth root of the value. So that's the problem for number 4. And again, this one's all or nothing, but it's probably the most calculations you'd ever have in one of these short answer problems. Questions on the short answer problems? Anybody unsure what maybe to expect? Okay, let's move on to the longer problems. There's going to be 3 problems, each with 25 points. These will have partial credit, so you can get anywhere from 1 point to full credit, or 25 points for each problem. So if I have 25 points to assign I'm going to expect, if you want the full 25 points, everything better be just right. But like I said, if you put down and just get started the problem, at least indicate that you know how to get started. Even if you get stuck, you'll get 5 or 10 points. Easily get 5 points just by showing sort of what you're doing. And if you're making halfway through, you can easily get 10 points. So do try to start each problem. Okay, problem 5 I like because it's an example where you're actually going to have to derive a differential equation. I wouldn't expect anything too complicated, but as you'll see in this problem, it's not, the result's going to look very familiar. So a drug is metabolized by the liver. So it's removed from the body exponentially with the time constant tau. Assume that at time t is equals 0, the drug is added to the patient's intravenous drip. So it enters the body at a constant rate. Let y equal the moles, the amount of the drug the body has as a function of time. So what we want to have a differential equation that governs y. So we want to know how y, the amount of the drug, changes with time. Now, there was 2 things it does. Well, does anybody want to suggest what the differential equation might look like before I start writing it down? You got an IV with drip, which putting in a constant rate. If you're putting in a constant rate, what does that? How do you represent that in the differential equation? C, just a constant. I'm going to use a different constant because that's what's on my notes. But I'm just going to call it A. Here's your IV drip. So if all there was an IV drip and no way to get rid of the drug, you'd start increasing the drug amount. But there's also says that the drugs are moved exponentially with time constant tau. Now, how do we represent an exponential process in a differential equation? How did we do it?
E to the...
Well, that's sort of the expected solution. But what differential equation gives you the exponential? Anybody? What's one differential equation? I said if you only know one, what would it be? Well, it's going to be that you have a derivative that's proportional to the function itself. In this case, it's going to represent a decay because it gets rid of it from the body. And it's going to have just y, but there's going to be a proportionality constant. And if you have a time constant, that usually is the proportionality constant, but you put it in the denominator, so the units work. So you end up going to get this as your differential equation. So again, looks familiar from what we've done before. You have 2 ways you can change the amount of drug in your body. You can have an IV drip, putting it in at a constant rate, or you can have an exponential decay of the drug, probably through processing through the liver or something. And that's going to fall off in proportion to the rate. The rate's going to be in proportion to the amount of drug. So, this would be an example where I might ask you to derive a differential equation basically from a word description. But surprise, it's nothing too complicated. It's what we've seen before. The same differential equation that we saw for Newton's law of cooling, that we saw for objects dropped through air with friction. Now, that's part of it. B, solve the differential equation in terms of A and tau, assuming no drug is present at t equals 0. So what's that saying is y equals 0 at t equals 0. So you come into the hospital, and the first thing they do is they stick you up. You don't have any drug present because this is a drug that you're sick. And they rush you in the hospital and say, well, you need some antibiotic, and you don't have any in you initially, and then they stick you to the IV drip. And now, what is going to be the solution? How did we solve a differential equation in class similar to this? What did we do? If I remember, Amber, do you remember what we did when we had the object falling through a resistive medium? Okay. Anybody gotta remember what we did? We guessed a solution. And we sort of know what the solution is going to look like because, well, it could be a constant. Constant will give you 0 for the derivative, so we'll say that there's a constant capital A, and we already know that it gets rid of this thing exponentially with time constant tau. So let's put in a time constant e to the minus t over tau. If you weren't sure this tau was the same as that tau, you could put in some arbitrary rate, and you'll find that the taus are the same. But this would be our guess. And then when we want to check the guess and find out what A and B are, we just stick it in. So we'll stick this in here. For the time derivative of a constant is just 0. The time derivative of this exponential, that's the beauty of exponentials. You get a 1 over tau from the chain rule, and you get the exponential back. So minus b over tau exponential. That's the left side. Then we're going to take the right side, and we're going to stick the same guess back into here. So the right side is going to have a little a minus 1 over tau times y. So 1 over tau times the whole thing is going to give us an a over tau, and then the minus sign will carry through minus b over tau e to the minus t over tau. Now at this point, I always say some magic words. Remember what you do at this point to figure out what capital A and capital B are?
Set the constants equal to constants and the exponential equal to exponential.
That's right. I wave my hand and I say this has to be true at all time. And the only way this is going to be true at all times is if the exponentials are the same. Well, the exponentials are exactly the same. So you almost cancel them out. And the constant terms have to be the same. Well, there's no constant term here, so this immediately tells you A is equal to A times tau. So we got A, but we didn't get B from this trick. Yes?
Where'd you get the negative b over tau e to the on the right side?
This is, when I put this in for y, I basically get a minus 1 over tau times y. And then I distribute the tau in, and the minus sign also, because there's a minus sign. And you distribute the tau in and the minus sign, you get a minus b over tau. Yeah.
Can you show how you got the negative b over tau on the left side?
On the left side, that's taking a derivative of this. The derivative of the constant is 0. The derivative of this, by the chain rule, the exponential wouldn't just give you the exponential back, it would give you minus tau from the chain rule times the exponential. So that's where that minus tau comes from, basically, for calculus. All right, but we didn't get B. So now, our last thing is we've got to figure out how to find B, and what was that trick? Really, telling me how to get B. Using the initial condition. So we already now know y is a times tau plus b e to the minus t over tau. All I did is stick in for a what I know. And we know that at time 0, y is 0. So y is 0 at e to the 0. E to the 0 is just 1. So you just get this relationship, which you can solve for b and get minus a tau. And now we have both a and b. They're almost the same. B is minus a tau. Capital A is little a tau. So y is, I'll factor the a and the tau out, and I'll get 1, that's from this term, the a term, and I'll get a minus sign, and then the b term, I factor the a tau out, e to the minus t over tau. And this is the solution to the differential equation in our case. And it's always useful. That question you just, yeah.
Where did you get the 1?
This one?
Yeah.
That is because a is equal to little a times tau, and when I factored the little a and tau out, all that was left inside was 1. Because I originally I could have put in a tau minus a tau times the exponential, factor the a tau out, and I get this. And then you can check this again. It sometimes takes 5 minutes to solve the differential equation, but it takes 10 seconds to check, at least to check the initial condition. 1 minus e to the 0, 1 minus 1, 0, obeys the initial condition. And it wouldn't take much work to take the derivative of this, plug it in here, and put in y, and just verify that indeed you did everything right and it works. So it does in fact work. It's the solution to the differential equation. And if I wanted you to plot it, it's not asked in this problem, but if you wanted to, y versus time, it starts at 0. Asymptotically, as the exponential goes away, you get a times tau. So it's going to approach a times tau, and it just approaches it exponentially. Where the time constant is when it's reached about 2/3 of the way to where it's heading. So that's the kind of thing you have. So this time constant, so you go, if you went into the hospital, tau. You went into the hospital, they hook you up to the IV, and then whatever this time constant is, that would kind of tell you how long it's going to take for that drug to really get into your body and begin to be effective. So sometimes hospitals might want to avoid this long time and give you a great big bolus right at the start, but that's a whole other issue. Okay. C. After a long time, what is the steady state amount of drug in the body? Well, we already figured that out. A times tau. You can either just put time equals to infinity here, realize that's getting real small, and you just get a tau. Suppose you had gotten stuck and hadn't even gotten the differential equation. Or no, suppose you had gotten the differential equation, but you were stuck with your guess. You didn't realize this was the guess. You're kind of stuck. You had no solution for y. How could you still find the steady state distribution of the drug? How could you answer part C after a long time? What's the steady state amount of drug in the body? Remember back in your homework? Somebody help me out here. Samantha, what do you think? If you knew this differential equation, but you didn't know its solution, could you find the steady state solution? Just, you're going to set dy dt equals 0. That's what it means to be in steady state. It's no longer changing. So if it's no longer changing with time, dy dt is 0, and you have a minus y over tau, and lo and behold, immediately you get y is equal to a tau. So you can get the steady state solution even if you didn't solve the differential equation. So don't completely give up if you're having troubles. Sometimes you can just reason out what part of the problem is, and always like to see this if you can reason out what the solution is, do so, even if you're stuck with actually getting a mathematical expression. Okay, that is question 5. That's a typical 25-point question. Again, I wouldn't go off and make you derive some differential equation that was really strange and odd that you've never seen, because it's a little bit beyond where I want to be. But you ought to be able to take words and describe them with mathematics. That's one of the skills I really want you to develop in this class, which is why I put it on the practice exam. Which is why you could see it on the final exam. Remember, these questions, cut and paste, are going to be on the comprehensive part of the final exam. Okay. Let's move on. I'm going to get some more space here, and we'll move on to the next problem. Problem number 6. Suppose a pore in the membrane has 3 states. State 1 with energy minus epsilon, state 2 with energy 0, and state 3 with energy plus epsilon. So this is a pore in a membrane. And it's a thermal equilibrium with temperature T, capital T. I want you to find an expression given the probability that the pore has 3 various energies. So basically, the probability that you're in this state, the probability you're in this state, the probability you're in that state. That's what you need first of all, and then, well, there's a few other things. So what's this talking about? What's the general idea that this problem is trying to get at? How do you begin?
Basically, probabilities in terms of C e to the kb over t? Or
It's the Boltzmann factor, yes. So this is a problem with using the Boltzmann factor, and we know that the probability of, let's say the probability, I'll call this the minus epsilon, so this would be, subscript would be the energy, is going to be C e to the, now remember, Boltzmann probability is one of the equations you're supposed to remember for the exam. So it's e to the minus, I'll do it this way, minus epsilon over kt. And the minus and the minus will cancel, and you get C e to the epsilon over kt. So it's a little bit strange that you get the energy of this state up here when you're finding the probability of the negative, but that's because there's two minus signs that cancel. And you can do the same thing. Probability of the plus epsilon state is going to be C e to the minus epsilon over kt. What's the probability of this zero energy state?
C.
Just C. It's C e to the 0, which is 1. So whatever you do, don't forget that e to the 0 is 1. So we now have the probabilities, but they're in terms of this constant C, and the question here specifically says, evaluate any constant of proportionality. So you're stuck. You can't just say, here's the solution, because I specifically said I want to know what C is. How do you find C? What's the trick for finding C?
Setting the sum equal to 1.
Yes, it's a process that sometimes goes by the name normalize, but you're saying you got to be in one of the states. Probability is 1 that you're in some state. So if you add these three probabilities, you get 1. So C e to the epsilon over kt plus, this state is just C plus, this state here is C e to the minus epsilon over kt has to equal 1. So that C, factor it out, bring it to the other side, is going to look like e to the epsilon over kt plus 1 plus e to the minus epsilon over kt. This is very similar to the homework that you're doing. So if it looks familiar, it's because it was on your homework problem. Basically, it's the same problem. Okay, so now you can plug this C into here, and you get probability. So I suppose you want to do the last step of it. P to the minus epsilon is C times this exponential. So it's e to the epsilon over kt divided by e to the epsilon over kt plus 1 plus e to the minus epsilon over kt. And you can also write expressions down for the other two states. And it's just the numerator that changes. Okay. Questions on that? I kind of went through it quickly, but it's a classic Boltzmann problem question. Yes?
So if every state is above 0, like let's just say 0, e, and then e to, or 2e or whatever, it would all be positive e to the, like there wouldn't be, or it'd all be negative.
It'll all be negative e. Yes, and that's actually interesting, because you might say to yourself, well, really, what does it matter where I take my 0 of the energy? But what you find in this case, to just kind of extend on your question, is that you can multiply top and bottom by like e to the minus epsilon over kt, and you'd end up getting exactly the same result for the probabilities. So in other words, this might be worth doing in class when you're at home. Try the problem 0, epsilon, 2 epsilon, and find the probabilities. And what you'd probably get, this is all my hypothetical problem here now. What you probably get is the probability to be in the 0 state is going to be 1 over e to the 2 epsilon over kt plus e to the epsilon over kt plus 1. This is exactly what you said, right? And then you can multiply top and bottom by e to the minus epsilon over kt, e to the minus epsilon over kt, just multiplying by 1. And now the result would be e to the minus epsilon over kt. This would be 2 epsilon over kt minus 1. So you just see e to the epsilon over kt plus this times this is 1 plus e to the minus epsilon over kt. And this would be the result for the lowest energy level, which would be got a minus sign off here. I'm not quite sure why. Probability of being 0 is going to be you might see why there's a minus. I'm trying to argue that these two are exactly the same, but I got a minus sign in the numerator that's slightly different. And I'm not quite sure why I have that. Because P to the minus E, that's the lowest energy level, so that'd be the ground state. Here the ground state would be E to the 1. Oh well, I have gone off on a tangent that I hadn't planned on. And you should get the same result. I'm not quite sure why I'm not getting exactly the same result. But to answer your question, if you had all positives, you would have, like you said, it would be minus sign in the exponential, right? You would get, here's why, you would get minus minus, because you had the Boltzmann factors would be minus signs of the energy. The energy is a positive, the Boltzmann factors are negative. So then you multiply by e to the plus over kt, and the same thing would work. E to the plus and e to the minus 2 would give you a minus, e to the minus and plus is 1, e to the plus would give you a plus, and then it's just switching the orders of the terms. You get exactly the same result. So it does work. I just got a little bit off. Okay. That part was sort of a digression, but I wanted to show you that what's really important is the ratio of these, how these energy states are related, and not the absolute value of the energy that you define. Okay. It's probably more than you really wanted to know when you asked that question. But, so then, let's see, what is the probability if the core is being in this ground state? Well, that's this probability right here. And then, what is the probability in this ground state if epsilon is much less than kT? Which means epsilon over kT is a small number. What would the probability of minus epsilon go to in this limit?
1/3.
It would go to, this would be approximately 1, because it's almost e to the 0. It's a real small number. This would be 1, 1, and it would all be 1, so it's 1/3. So you're essentially finding that a third of them, and when it's hot, epsilon is much less than kT, you have a third here, a third here, a third here. Now if you wanted to get a little more accurate, because it's not exactly a third, there's going to be slightly more down here. If you want to be a little more accurate, you approximate these with the Taylor series. And then you could get sort of the next order term. But that's not really what was asked in this problem. It was asked for this result. Then what if epsilon is much greater than kT? So in this case, it's a very, very cold system. If epsilon is much greater, so epsilon's a big number.
1.
Yeah. So epsilon's huge. So this is a giant exponential. Well, this is a giant. I should be looking at this one. This is a giant exponential, much bigger than 1, and vastly bigger than e to the minus huge number. So it's essentially this over this, which is 1, and you're finding that they're all in the ground state. So when it's cold, they all go down to the ground state and sit there, and none of them go anywhere else. So you can solve it in this way. Yeah.
So, I mean, couldn't you technically answer all those 3 questions without the equation?
You could easily guess these 2 limits by just saying, oh, they'll distribute themselves equally in this case, and in the cold case, they all go down here. So if you for some reason forgotten what the Boltzmann distribution is, it's an example of where you could still answer part of the question. But I don't think you could get the, if I specifically asked you for these probability expressions, I think you have to know the Boltzmann part in order to do that. Okay. That is problem 6.
Explain why the ground
Say explain.
Why is the ground state crazy probably?
Well, I can explain it two ways. I could go through and we can look at all these probabilities and you can probably prove it. But in general, you have an exponential, p to the minus p is equal to e to the minus e over kt. So if you plot that versus energy, the probability, you're going to get something that looks like this. And it doesn't really matter how fast this falls off. No matter what the energy is, you're always going to have your biggest value here at the lowest energy. I suppose if this was going to negative energies, it'd still go down. But the point is, if you have discrete energy here, here, and here, it's always going to be biggest in the ground state because of that exponential factor. So that's one way to just make the argument. Now, you have to be a little bit careful if you have non-degenerate states. Suppose you had low ground state, two states here, and a state here, and then you wanted to know the total number in each energy level. And then you might cook up a situation where there's more in the middle one just because you had degenerate states. We're probably not going to run into, the only place you might run into degenerate states are these problems where you have concentrations, where you translate probabilities into concentrations, but that's the only case I can think of where you might find that the ground state isn't the most populated one. And then it's really because you're adding up the sum of the two to get the total probability. The probability in each individual state is still going to be highest in the ground state. It's just that if you ask for the probability of being in this energy, you get twice as good. So clearly at a high temperature, you get 1/4, 1/2, 1/4. You have more in the middle state. Other questions about that? So, the nice thing about this is you just basically did one of your homework problems that you're taught to hand in. So let's go and look at the next problem in the list. Okay. Now, this is always a treat for the students. We're going to do the arabesque position, which I will try to demonstrate. Something along this line, which I'm obviously not a dancer. But we're going to be looking at the leg. And this is the biomechanics. This is from day 2 of class, where you're looking at all the forces on the leg. So, in the ballet, the arabesque position is shown below. Let us focus on the forces on the horizontal leg. There's a weight of the leg acting on the leg center. So this is a little bit different than some of the past problems. In the past problems, we were saying, like, if this was an arm, you're holding a big weight out here. But now we're saying, well, you're not holding anything out here, but the weight of the leg itself, acting from the center, is W. So, and I say specifically acting on the center. The force on the hamstring muscle, that's the muscle right back in here. That's the muscle that you're exercising in the arabesque position. That's going to be here. And it says it's a 15 degrees. And it says it's called T. And it's acting 1/4 of the way along the leg. So here, that's 1/4. That's 1/4 of the total length. That's the total length. And there's also the hip. The reason why your hamstring doesn't just pull your leg, shoot it out, is because the hip's pushing back on it. So the hip here, which I'm going to draw as a little hinge, because that's where the leg actually hinges, is pushing back. We don't really know the direction of that, but we'll just call it F, like this. Okay, now you're supposed to find T and F. So, in this case, we're finding expressions because we're not actually told what the weight of the leg is. How would we begin? What's the first thing you usually do in these problems?
Why doesn't the problem say like 10 degrees instead of 15?
Oh, this is the one that I didn't... say that again?
Here it says T is 10 degrees. Wow.
Huh, okay, this was a typo long ago. I fixed it in the solution I'm sending you. I happen to be reading off of that solution. But the thing that got sent to you guys, I forgot to fix. So that's technically, let's say that it was a typo and it was 15. Obviously, if this happened on the exam, I'd grade the problem that I gave you. But I'd forgotten to fix this. That's why I got so confused. In the paper I have here, it says 15. So we're going to call that 15 degrees instead of 10. And okay, besides that issue, how does one get started? Remember, the first thing you had to do is you had to define a coordinate system. So this one, when the thing is sticking out horizontal or vertical, the coordinate system is pretty easy. It's horizontal and vertical. We'll call that, and we'll call y down. Doesn't really matter if it's y up or down. What are the basic equations that we're solving now? It's going to be the equations of static equilibrium. So if you're in static equilibrium, what's that mean for the force? What's the sum of the forces equal to? 0. It's F equals ma, but a is 0. So we'll start with the x direction. There's no force of W in the x direction, so that doesn't contribute. This one, t points more generally in the minus direction, so you get minus t, and what's the component in the x direction? Cosine. Cosine of 15, because it's the adjacent. It's along the axis. And f. F's a little tricky because we don't know its direction or its magnitude. So what we usually do is we divide f into two components, Fy and Fx. And since we're finding the forces in the x direction, you're just going to get plus Fx. And that's going to give you 0. And that is the first equation. Remember, if I ask you for a vector, you can either give me the components or you can give me the magnitude and direction. You don't have to do both unless I specifically ask for it. In this case, it's a lot easier to do the components. Okay. Y direction, what do we have?
W minus t sine 15.
Okay. W is going down, and we have this one's going up, but since I think down is positive, it's minus t sine of 15. And then there is this Fy, which is plus Fy equal to 0. So I've got two of them. It's a two-dimensional problem, which will be a problem on the exam with the two-dimensional problem. And I've gotten the sum of forces in both directions is equal to 0. But I've still got three unknowns, t, fx, and fy. So what else do I need? Torques. Torques. So let us take this direction to be positive. I always take the torques if possible. You don't have to. You take the torques about 8 point. I always find it particularly convenient to take it around the joint, mainly because that's the natural rotation point. So it's intuitive to me. We don't know what the length of this leg is, so we'll call that L, but we do know that this is L over 4 out to here. So it's 1/4 of the way. So let's begin. What's the torque from F? Nothing, yeah. Both of these go right through that point. There's no moment arm. The torque from this force. Well, if you divide this into components, the component in the x direction goes right through the point, so it doesn't contribute anything. It's only this component in the y direction, and that's going to tend to rotate it opposite, so minus t, and the y direction would be sine 15 times the moment arm, or the distance, that's this distance, L over 4. This one's easy because it's already pointing in the y direction. It's going to make it go in the positive direction. It's going to be W. And this one's going to be L over 2. And that's it. And that's equal to 0. So, if the only thing you get done is this much, you're going to get at least half the credit for the problem. But now we have to solve for t, fx, and fy. Anybody want to offer a suggestion of how to start?
With the torque.
Start with the torque equation because it contains only one unknown. This term is, we're assuming W is known as the parameter. If we're going to solve things in terms of W. So we can just solve for T, which is the L's will cancel, and the T comes to the other side. We'll bring the sign, we'll bring a 4 sine of 15, or actually we'll bring the sine of 15 downstairs and the 4 upstairs. So you get W, you're going to get 4 over sine of 15, and then you got this 2 that's still in there. So you're going to get 2W over sine of 15, sine of 15. So it helps to have a calculator. Just do make sure you know degree versus radian modes and use the appropriate one. You get 7.7 W. Same thing as on the homework. If you gave me 7.76543632, I'm not going to take off points, but I'm going to write a algebra mark in red saying that's way too many single figures. Okay, so that is T, and then you can find Fx by just plugging T into here and solving it, Fy by plugging T into here and solving it, and you got W. I'll just write down what those are since I don't want to go through the entire algebra. 7.4 W Fy is equal to W. And the real biological implications, which you didn't specifically ask for, but the point is, why is ballet a pretty difficult sport, if you will, or dance? It's because, look at these forces, 7 times the weight of the leg itself. So even though your leg isn't a hugely heavy, you have a much larger force that the hamstrings have to do. In fact, if I do this properly, I should feel it in the hamstrings as I do that. Okay, questions on that problem? It's a little more difficult if the problem is, if I was doing my version of the arabesque, since I can't really do it, I'd probably have the leg down here at some angle. And then that would actually be a little more difficult to do, because then you'd have to do probably X and Y, and now the weight of the leg would be at some angle. Let's say you have a little bit more difficult problem, but not unreasonably more difficult. We did that when we were looking at the lifting of objects. So you should be able to handle even problems a little more difficult than this arabesque. Okay. Now, last problem is essay. Write down the Boltzmann factor, explain what each symbol means, describe physically, not mathematically, under what condition this factor applies, give an example of how the Boltzmann factor plays a role in biological physics. So, in some ways, I'm asking you to write down one of the equations that I told you had to memorize. So that's the first thing. So you should say Boltzmann factor is P is equal to C e to the minus E over KT. And I'll just tell you what I had here. The Boltzmann factor determines the probability that the system has an energy E. It applies to system. What is the condition you have to have in order for Boltzmann factor to apply?
Thermal equilibrium.
Thermal equilibrium. So if you're not in thermal equilibrium, you don't really have this. So if you sometimes it takes a while for thermal equilibrium to be established, or sometimes you have problems where you have energy coming into a system and it's not really in equilibrium. Boltzmann factor wouldn't apply, but it does for thermal equilibrium. And this has non-degenerate states. You can go into a little discussion of what degenerate and non-degenerate states are if you wanted to, although probably you get full credit if you didn't even bring that up. And then you'd have to say what these different symbols are, because I asked you what the symbols are. That's the probability. That's some constant. Probabilities are always dimensionless. So this is the E from the exponential. That's the energy of the state, Boltzmann's constant, and absolute temperature. You probably should say that there has to be the absolute temperature in Kelvin. Okay, we talked a bunch of examples which you could draw from. You could talk about the pore in the membrane that has various states like you did in the homework. You could talk about the atmosphere. You could talk about MRI, which is the very first example we did. We did several examples. The book had some more too, catalysts and whatnot. So if you do that much, you should probably get 5 points credit. Try to put it in reasonable words with not too many grammatical errors. But like I said, I won't be grading hugely on grammar. But maybe there might be a point in the balance if you start giving me something that's just unreadable. Yes?
You said that an electron switching states is Boltzmann, right?
An electron,
Like switching from different energy levels, like a hydrogen atom.
yes, that would be Boltzmann if you were in thermal equilibrium. That actually brings up an interesting question. What's an example where you're not in thermal equilibrium? A laser is an example, because a laser pumps energy in and pumps electrons up to the higher level, and then they fall back down. You do not have a Boltzmann distribution and something like that, where you're pumping energy in and then pulling it out. It's got to be something that's in thermal equilibrium. So that's the key. Yes?
So are you expecting like multiple like paragraphs for these type of questions,
Well,
or just
when you look at my solution, which I'll send around Friday morning after class, it takes up the space right here at the bottom. So it's basically one paragraph. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about 15 lines. But some of those lines are just P is equal to one line, C is equal to another line. So there's about 8 or 10 lines of text. So no, I'm not expecting a huge thing. If you find yourself writing a whole page, it won't hurt you. However, there's one thing to keep in mind. If you find yourself writing stuff that you're not sure about, you could hurt yourself, because if you leave something out, like you didn't say anything about degenerate states, well, that wasn't specifically the problem. I'd probably give you full credit if you had all the rest of it right. But if you said something about degenerate states that's wrong, you're probably going to lose a point. So don't go off and try to create too long of a thing where you're not sure what you're talking about, because that could end up hurting you. So that's practice exam 1A. I don't have too much else general to say about it, except that you're going to find the format and the structure of the exam is going to be almost exactly the same. We went through this whole thing slowly together in a little less than an hour, so you have a little more than an hour to do it yourself. Friday, we're going to start working on the other two practice exams. We're going to either have to go faster or we won't make it through the third one, but you will get the solution. So if you do going through the practice exams and you find one, say a problem on the exam, practice exam 3 that you really wanted to have solved, or see, whatever it is, you might want to bring that up and then raise your hand and say, can we skip forward to that, because we might not get through the last two on Friday. If you haven't gotten your homework back, 1 and 2, I have them up here. Otherwise, homework's due Friday in class. Yes.